Hey guys, so today I'm going to be going over this learning objective 14.4.2, which is the parts of an electrocardiogram and then how they relate to the mechanical events of the heart. So we're going to start off with this figure from the textbook. The first thing we're going to start off with, which you're going to see all the way on the left of kind of this whole thing, which is one cycle, right, of the heart. This is the P wave, so it's going to be this first little bump before you get the big spike, and then the P wave is happening during atrial depolarization, and then that is going to lead to the contraction of the atria. So that's just right here, this little P wave. Then you have an interval in between the very start of the P wave and the start of this QRS complex. They call it the PR interval because sometimes there's not a Q wave in an EKG, but you're always going to have an R wave if you're getting any response from the ventricles. So then you have your QRS complex, which is this little dip being the Q wave, this big upswing being the R wave, and then you come down, and this again, another dip down is the S wave. And then this whole segment is when the ventricles are depolarizing, and so the ventricles are contracting because of this electrical conduction. Then finally, you're going to get the T wave. So the T wave in this figure, it's looking really small and kind of very similar to the P wave, but in most EKGs, you're actually going to kind of see a bigger bump for the T wave. It's not going to be so short and small like the P wave. It's going to be a little bit bigger, so don't get thrown off if you see that. It's very normal for the T wave to be a little bit bigger than this. And the T wave is ventricular repolarization. So this is kind of the relaxing and resetting of the heart before you go into, again, the next sort of heartbeat.
Hey guys, so I wanted to talk about the pressure changes and in the blood vessels throughout the cycle and the relationship of the heart rate and the cardiac output and stroke volume. So that's what that is. And so we're going to go to the next slide. Next slide, we're talking about the cardiac output, heart rate, and stroke volume. Cardiac output is equal to the heart's stress or the stress on the heart measured in liters per minute, and the heart rate impacts that because it's per minute, and basically, and then your stroke volume is equal to your end diastolic volume minus your systolic volume. And so you multiply those together and you get your cardiac output, as we see down here in the right hand corner. And then next we have the pressure changes in the size area of vessels. Basically, as we have a bigger cross-sectional area, we have a smaller pressure, and we have the highest amount of pressure in our artery and arterioles. And also the speed that it goes through is a lot faster. And basically, there's sort of an inverse relationship there that we can see. And then I wanted to have an example and talk about cardiac output as an example. So bringing in a friend of mine. Today, I wanted to talk about the escape of Bobo Baggins as he stole my precious from me and hid it in his stupid fat pockets. His heart rate was very high. Too bad that his cardiac output didn't get up high enough to kill him. But he was able to escape, and because so his cardiac output went down, because his heart rate went down, because he's no longer trying to escape from me. And the annoying little to spare my life, but I wish he died. And basically, as you see there, perfect explanation from my friend Gollum. And hope you have a good day. Come on, there we are.
Hello, my name is Sophie Danes, and today I'm going to be presenting on myocardial cell action potentials, the difference between the two of them. In the myocardial contractile cells, the muscle cells of the heart that contract, they have similar action potentials to neurons and skeletal muscle, they're almost the same as the ones we're already familiar with in those. They begin with the rapid depolarization that comes from sodium entry, and then a steep repolarization that comes from an influx of potassium. The major difference is calcium. The cardiac muscle cells will have an influx of calcium that makes the action potential last longer, making the refractory period and the action potential about the same length. Between depolarization and repolarization, there is a plateau where the action potential is more flat. And this is what extends the length of it. And that's as calcium permeability increases and potassium permeability decreases. And then repolarization happens when the calcium channels close again and potassium exits the cell rapidly in a typical repolarization, just like the other kinds of cells that we're familiar with. And so these are graphs that show what that looks like. You can see over here, you start with the sodium channels opening, and that leads to this depolarization. And then the sodium channels close. And we have the plateau here, where the calcium channels are opening and the fast potassium channels are closing. And this is the extended portion, the plateau. And then we get back to our repolarization here as the calcium channels close and potassium open. And this shows what the contraction looks like next to the action potential. And this is what prevents tetanus in the cardiac cells, which is really important because in skeletal muscle, it can be helpful to have repeated action potentials summing and holding a contraction, but it's important for the heart to contract and relax continuously to do its job. And so that's why not being able to have tetanus in that summation is important, and why the action potential and the contraction length are similar in cardiac muscle cells. Um, in autorhythmic cells, we have, rather than a standard resting potential where the membrane potential rests at a constant negative 90 millivolts, we have an unstable membrane potential that begins at negative 60 millivolts and slowly just kind of drifts upward towards threshold without external stimulus. This is due to the funny channels. Funny channels are different from channels in other excitable tissue. They're permeable to both sodium and potassium. And just over time, the membrane potential becomes more positive as the sodium and potassium come in until it reaches a certain point, and then calcium channels open, and that brings it to threshold. Once it's at threshold, there's a different subset of voltage-gated calcium channels that open, and that causes the depolarization instead of an influx of sodium like in other excitable cells. Repolarization is then due to efflux of potassium as it leaves, similar to other cells. And this shows, I should erase this. But this here shows as well the pacemaker potential of this slow kind of rise, and then the action potential that comes as calcium comes in. So yeah, that is all. Thank you.